Greetings, the Astro30 here yet again, and welcome back to the Amplifier channel. Welcome back to AEL. Now, if you're new to this channel, please consider going below and subscribing if you haven't done so already. Cheers. Well, today we're going to bite the bullet and we're going to build up this amplifier circuit published in the November issue 1995 of the Elektor magazine, which has been stolen on the internet by other people, and test that it works. This IC here is being used as a differential amplifier in the differential or difference amplifier op-amp configuration, except it's missing its local feedback resistor between pin 6 and pin 2, which would be the same value as this resistor down here in the negative feedback path that's being used by the amplifier. Now, I've tried to test this IC circuit on its own without that resistor, and it does nothing until you crank the input signal up, and then this just slams square wave rail to rail. So that's not really practicable in testing on its own. It most likely needs all of this extra circuitry on its output side for this in order to work as a differential amplifier without local feedback. So I have explained the operation of this circuit in another video, which is linked in the description, but I'll go through basically what we're looking at here. That's the differential amplifier, as I have already explained. These two transistors here is what's known as a push-pull voltage amplification stage. This here is the bias spreader circuitry, which adjusts the bias to the output stage. These two transistors, along with these four diodes, these two 27K resistors, these two 1K resistors, and these two 150 nanofarad capacitors are the VI limiter, which limits the current to the output stage in a short circuit condition. To what actual current value, I don't know offhand. But when I'm building this up on breadboard, I'm going to ignore this circuitry. I'm not going to include it just yet because, well, I don't really need to put this on here to test the validity of it passing an input signal to its output. Here are the driver transistors, and this is the output stage, and this is configured as an emitter follower amplifier. We've got emitter degeneration here and here. The problem with the VI limiter, however, is we're measuring across just two of the degeneration resistors and not both. Obviously, we can't short to there because then we're bringing these two resistors in parallel, which is going to halve their effective resistance, which is never a good idea. One modification I'm thinking of doing is we can leave these two resistors here in the emitters of this transistor, and then we bring the emitters of these transistors to the emitters of these transistors, and then we put two extra degeneration resistors in the collectors. That is one method of doing it, and it should work fine. It's just the same principle as using a complementary feedback pair or C-clay complementary compound pair. The same way of mounting the collectors directly together through two degeneration resistors like this, and putting two extra emitter degeneration resistors up in the positive and the negative rails respectively, and it achieves the same thing. That just means that now this VI limiter is measuring the current across just these two resistors here and both output devices, which is something I'm going to consider. I'm also going to replace the value of these two diodes here, BY254, because, well, I did some cross references, and a 1N5408, which is a 1000 volt 3 amp diode, will do just fine here as the flyback diodes. The other modification is obviously these power supply rails are going to be reduced to plus minus 42 volt. I think it's just easier on the transistors, and I don't really see the need to have this supply voltage that high because I'm not really interested in producing 300 watts into 4 ohms. If I can get 150 watts or 200 watts even into 4 ohms, all well and good. However, in this video, I'm not going to be building this to get its power output measurement. It'll have to be put on a proper PCB and run at the correct supply rails that I intend to use before I can get a power output measurement. So the idea of this video is to just test whether or not this circuit actually does work. And it should, because considering if we go down further a couple of pages, he's already made a PCB for it back in 1995, and I can assume that probably hundreds of thousands of these have been built at home by readers of this magazine, so it must work. There's no reason why it wouldn't work. It's just the configuration of IC1 may seem a little bit strange or unusual to the average person. The differential amplifier is supposed to be amplifying the difference between both inputs. So both these inputs need to be a different signal source. So in the terms of the amplifier, it's measuring its output, which is one signal source, and comparing it to its input voltage, which is a completely different input source. And what all op amps try to do is it tries to make both these inputs the same. So when it's doing that, it's correcting for any distortions on the output so that it makes the output basically follow the input, only it's much stronger. So without further ado, I'm going to build up all this complete circuitry here, bar the VI limiter as already stated. We don't need the relay circuitry in there because we know that works separately on its own, and test that this actually passes an input signal back to its output and is actually amplified and is clean, undistorted. And we may do a power measurement on a low supply of plus minus 18 volts just for giggles. I may ramp it up to plus minus 30 volts just to see how much more power we can get out of it, and then probably predict how much the power is going to be at the plus minus 42 volt rails. We also want to see that the bias is adjustable, and I may have to modify this input circuit here to include the offset null components, which is a 100k variable trimmer between pins 1 and 8, and the center of that trimmer, it goes through a 22k resistor to the positive rail, in this case the 15 volt rail here, to just offset null adjust the input. Because reading the text of this, he says there is roughly between 20 to 30 millivolts normal DC offset on this output. However, that can be greatly improved and reduced. That's something I'm going to be experimenting with. I'm probably not going to worry about this clip output because, well, you need a separate clip detector circuit for that to even be valid. I may, if I decide to make this as a PCB, include that just because it's there. But yeah, you'd have to use a separate module that detects the clipping on this output. However, I digress. Let's get this built up on breadboard, test that it actually works, and then move on with life. Oh well, my parts from DigiKey in America have come today. The transistors and stuff that I need to basically do an experiment. Yeah, it's just what it is. I mean, I made sure that the order was like $60 odd. That way I actually get free shipping. So it only cost me about, what was it? About $67 in the end, total. And they've really made it so you can't get into the bloody thing. So, okay. Interesting substance that. Just got to make sure that there's nothing there that's going to show my information, so I'll make sure to remove that out of the way. Okay, so that can go in the recycling bin. So what have we got here? We've got 4 of them for some reason. 470 picofarad, MP0 or C0G, 250 volt radial multi-layer ceramic. Okay, I've got 4 of them, I only needed 1. Got some like 1 N5534-Based, which is 1000 volt 3 amp diode. Yes, good. I got 10 of those. They're for the flyback diodes. These, this is just a trim pot, 250 ohm trim pot, because I can't get them in Australia. Yep, 250 ohm. I like the fact that it's in this plastic, no, rubber actual holder thing, so, and a plastic tube, so it doesn't move around. Alright, let's see what we've got here. MJ350, I've got 4 of them. PA300 diodes, they're Schottky diodes, they're used in the push-pull VAS, and they have like a 3 volt drop instead of a 0.6 of a volt drop like normal signal diodes do. I've got 10 of them also. So it's very important to use the right diode there. 30 volt 200 mA. MJE1531G, which is one of the drivers. TO220. I got some NE5534-Based op-amp circuits. I think I got 3 of them or something, I think it was. MJ340, I got 4 of them. TIP36C, 2 of them. That's for that other AEL 2011 power amplifier. I think I said 36C, not 35C, but whichever. I've got the 35C as well. No, that's an MJ1531 TO220, they're drivers. Oh, there it is. And finally the TIP35C, and both cases are the same. Isn't that special? There should be TO247-3, which means it's got 3 legs. So excellent. I've got all the crap that I need to build the experimental amplifier. Plus, this is what I was actually ordering from DigiKey in the first place, was these output transistors for the other module. But I've got to wait for the PCB to be remade for that. It's currently in manufacture. So now I'm going to spend the next hour or two painstakingly breadboarding this circuit out, just to see if, well, it actually works. And so, bought all these components just to do one thing. Yeah, that's what happens sometimes. But yeah, word of advice, if you're going to order from DigiKey, you've got to order more than $60 to get free shipping, otherwise it's just not worth the effort, because it's $24 flat shipping. So if you only want like $20 worth of stuff, you're going to have to pay the $24 shipping, so you're paying $44 in the end. So it is probably a good idea that if you're going to order stuff from DigiKey or Mouser, they're the same. Not sure how much you have to buy from Mouser before you get a discount or free shipping. But with DigiKey at least, $60 minimum spend, and the shipping is then free. So yeah, I'll get to about breadboarding this circuit out and testing that it works. Fun. It's quite a complex, well, it's not complex, it's just you know, one of those things that you just want to do later, not right now. But anyway, I've got the parts to do it, so might as well do it. Greetings, the Astro 30 here yet again, and welcome back to AEL. Wait a minute, we've already done that. No, seriously, I've got the circuit built up. It's actually the next day, because I didn't really have time yesterday to build it and test it fully. But I will admit, I've already tested this off camera and found a couple of problems immediately. And I've got a solution to one of those problems, but I'm going to go through the testing procedure on camera. The reason I did the preliminary tests off camera is so I know where I'm going at this point in time and not making a complete you know, hash of it. So the first thing I want to do is just explain the circuit layout here. These are the shunt regulator diodes and dropper resistors for them. There's the NE5534 IC with all its input circuitry configured as a differential input stage. These two transistors here are the MJE350 and 340 respectively. They're the VAS transistors, or you could call them pre-drivers, I suppose. Next to that, we've got the VBE multiplier or bias spreader and all its components, plus the 470 picofarad NP0C0G style multi-layer 250 volt multi-layer ceramic, which I really don't think it needs to be 250 volts or a multi-layer, but the original circuit called for polystyrene capacitors, and they're almost next to impossible to find these days. Up there are the MJE15030 and 31 respectively, and they're actually very shiny. They've got like a shiny body on them. See, if I move my finger there, we've got a light reflection there. They're very reflective. I've never seen a transistor like that before, and they both do that. Just above those we've got the degeneration resistors, the blue ones, and the Zobel network, the 10 ohm and the 33 nanofarad capacitor respectively going to ground. And back there is the output stage, only 2 transistors for this test. I haven't got the full set of 2, it's just a single pair. They're the Toshiba 2SA and 2SC transistors I've had knocking about. They seem to work okay for these tests. Well, at least I haven't blown them up yet. So the first thing I'm going to do is I'm going to turn this bias pot all the way fully counterclockwise so that the pot is at its maximum resistance and the bias current is at its minimum because of the way the pot is configured. And I've been turning that all day, so I'm pretty sure I've gone past the 25 turns and it's not making a clicking. Oh, there it is. It does make a clicking sound. Nice. I didn't think it did. Anyway, so that's now at its maximum resistance, minimum bias. I want to take my multimeter leads and I want to connect to the output point and ground and just measure the DC offset. So I'll just want to ground somewhere, that should do for the testing. Got my power supply set to roughly plus 19 volts, minus 19 volts, or 19 volts each side. Whichever way you want to look at it, turn it on. No unusual current draw. And immediately we can see we have a minus 12 millivolt DC offset there. So it may need the offset null components installed on the circuit. Jesus, meter has a real hard time ranging. Maybe because the speed's on high. And yeah, that's a bit better. So yeah, we're about 14 millivolts minus. I'll stick that back on high because I like it going high. And stick it back to volts. So yesterday when I was testing this, it was closer to 0. So it's sort of jumped up in the meantime. So far so good. Yeah. When I touch the input with my finger, we can see that that is jumping around. So that's indicating to me that it is actually working as an amplifier. Alright, very good. So I'll turn it off. And I'm going to now insert a 100 ohm 5 watt resistor, my safety resistor, in series with the power supply positive rail. And I'm just going to measure the current, or the voltage drop across this resistor, and convert it to current. So we know how much the circuit is drawing, and then we'll see if the bias is adjustable. Okay, resistor is in circuit, or in series with the positive supply rail. So turn the supply on. No unusual current draw. And currently we're sitting at 2.8 volt DC, which is the equivalent of 28 milliamps of current running through the output stage. Well, running through the rest of the circuit as well, just as a note. So I'll turn my trim pot up and see if I can get that voltage to adjust. Which, by the looks of it, not much is happening. I've turned it quite a considerable way. I'm about halfway now and it still hasn't changed. Because actually in the text it says he wants this biased at 100 mA, which I think is a little bit high. But I'm almost at the end of the travel of the pot and that voltage is not changing. And I'm still turning it. And that's the end stop. And it did not go up. If anything, it went down by about half an MA or something like that. Okay, so that's the first problem that I discovered. So that may be because the voltage supply rails are too low for the values of components in this bias spreader to work correctly. So I'll try it at plus minus 30 volt a little later and see if it's adjustable. If not, then I will modify the bias spreader components until it does work. I'm just going to turn this all the way back down, which may take quite a while. There it is. Okay, moving on to another test. Now, considering I know that it's got a reasonable current draw and a reasonable offset, it's safe to assume I can actually connect some test equipment and an audio source and just see if it is actually passing an audio signal. So that's what I'm going to do now, after I turn the supply off, is I'm going to connect my oscilloscope to the output and ground in times 10 at the moment, which is fine. Find a reasonable ground, which is down here. And I'll connect my oscillator and set all that up. I might remove that safety resistor out of circuit as well, because it's not needed for this part of the test. So that gets put back there. This comes in around over to here. I've got to walk around the camera, that's the only problem. That gets connected to here and here. Let's turn the oscillator on. I'll set up for 1 kilohertz, my favourite song. That was wrong, that's 10,000 hertz, 1000 hertz. Run the oscillator, yeah, give it a bit of gain. Alright, turn it on. Well, according to the scope screen, there's not much happening. Absolutely nothing happening. I know why. That's not the supply lead. I was getting minus 20 volt across the multimeter and wondering why. That's because I've still got the power supply going through the resistor to the negative of the multimeter, and I had the positive probe of the multimeter connected to the positive post of the amplifier, which is not going to work. Let's try that again. Oh, there we go, we've got an output, but oh my god, look at that. That's ringing badly. Or oscillating. Yeah. That is a problem. Quite a big problem. In fact, when I drop the oscillator right off, look at all that noise. That's mostly just oscillation. Okay, that's an issue. Well, as I was messing around with the circuit touching things, the ground wire for the Zobel network actually came loose and flew off. And wouldn't you know it, it's corrected the signal. It's no longer ringing. Which is odd, because the Zobel network is supposed to prevent the amplifier's output from ringing, not cause it. So that is strange. So let me just reconnect the ground, and there's our oscillation. And if I remove it, it goes away. Okay, so I'll reconnect it. Now I'll change out this 33 nanofarad capacitor, which the ringing's now stopped, for a 100 nanofarad capacitor, which is what really should be in the Zobel network, or even 220. And well, it is a bit better, but it's still not great. I do know a better fix for this, but what I do want to try is swapping that 100 nanofarad out for a 220 nanofarad to see if that makes a difference. Okay, so I found a 0.22 or 220 nanofarad out with the 100, in with the 220. If I can get it in there, it'd be nice. Well, yeah, it's still got a ringing there, and it'd be silly to go to like something like, you know, 330, 390 or even 470. That's just too large of a capacitance for a Zobel network. It should be more like 100 nanofarad. So let me actually do the fix that I found actually corrects the problem. So first I'll take this 220 out. I will go back to my original 33 nanofarad, which is there. No, it's actually there. Get in there. Alright, we've got some ringing happening. Over here at pins 5 and 8 we've got a 33 picofarad capacitor. If I change that to a 10 nanofarad ceramic, because that's the frequency compensation pins, if I can get it in there, be nice. Alright, boom. Isn't that special? So if I disconnect my Zobel, it does actually clean up a bit better without the Zobel. Plug the Zobel in, if I can get it in. There's still a slight ringing there, so maybe if I change back to the 100 nanofarad capacitor, which is what I was mucking around with yesterday, and then leave it at that, as we can see, that, well, it's pretty stable, and that's the way it should be. So there's one problem. So why was the circuit doing that? Well, one, the ceramic capacitors that the ones I'm using, that were the values that were in the original schematic are actually supposed to be polyester, as I stated with this weird capacitor over here. And that is probably the reason why polyester was used, to keep the circuit stable. So he must have mucked around, especially with the capacitor across the feedback resistor, with various different values of capacitors and types of capacitors, to actually get the thing stable. But me putting a 10 nanofarad ceramic in the frequency compensation pins of the NE5534 seems to clean that up. So I'm going to turn the oscillator, I'm going to stop the oscillator. What I'm going to do is I'm going to connect my multimeter back between output and ground, and I want to see what our DC offset is now with the thing not oscillating. So, because that may have skewed the result. So I'll just connect the meter to there and ground. Almost bugger all. So I'll disconnect the scope just in case it's loading it. No, it's absolutely bugger all DC offset now, which is good. So I might power cycle it to just see whether or not as soon as it's powered up, well, it has warmed up now, so that may be another thing too, but power it on. Nah, DC offsets is still good. 1 odd millivolt is perfectly acceptable. Okay, moving on. Should I include the DC offset null components? Probably. I've got some space over here I could do that with. Is it necessary? Not at this point, no. Is it a good idea? Still yes. The other thing I haven't included on this layout here is the VI limiter, because it's not necessary for these tests, as I already said in the beginning. I don't have the output choke installed, which is the resistor and the inductor in parallel, because, well, they're really only needed when you're trying to drive really long speaker leads and it becomes capacitive, which is the reason why I believe the Zobel network, when its original configuration, was causing this to ring. It was actually causing the input stage to ring, because it was capacitively loading the output of the amplifier, turning it into basically an oscillator, which is what that coil is supposed to do. Unfortunately, the coil would normally be on the other side of the Zobel network before the output, not where the Zobel network is actually connected. In other words, the Zobel network is not actually connected after the coil, it's connected before. So that would have done nothing. So, now the issue of the bias. As I said, I reckon it may be the supply rails are too low for this bias network to actually do anything. So what I might do is I might up this to plus minus 30 volts, and I'll keep the meter connected to the output so we can see what's going on. See if the thing blows up. If not, all well and good. And then try adjusting it again. Okay, I got the supplies hooked up in series with each other, and I've got this set to a current limit of 100 mA. This one I don't know what it's set to as a current limit. So as they say, stand by for blowing up and laughing. Okay, no unusual current draw, nothing went off with a bang. Currently about 13 milliamps of current being drawn from the amplifier, which is okay, and our DC offset is still good. Alright, is it still working as an amplifier? Let's find out. So I really should turn this off first, but I'm going to carefully connect this to the output point and ground without disturbing too much. Okay, turn the oscillator back on. Oh yeah, still working as an amplifier. Excellent. Right, so let's see now if the bias is adjustable. Resistor is back in series with the positive rail, and I'll turn the supplies on and we'll see what the voltage drop across that resistor is. Minus 1.6 volts, but it's probably because the leads are backwards. Yeah, it is. I've got the negative lead going on the incoming positive supply, so that's okay, that's fine. We'll ignore the minus. The current has actually gotten less with the higher voltage, which is interesting. So I'm going to see if rotating this potentiometer does anything. Oh yes. Yes indeed. Nice. Okay, we're at 20 mA. Power supply says 17, 18. I wonder how high this can actually go. So 25 mA, 26, 27, 28, 29, 30, 32, 33, 34. I slipped out. That's what she said. Okay, at this supply voltage it looks like 34 is the maximum. But that's perfectly fine. So this was definitely designed for plus minus 60 volt rails. So in the end, with my modification of the 40 plus minus 42, this bias servo should be good enough to get this to around the 30 mA mark. So what I'm going to do is I'm going to let that stabilize for about 5 minutes or so, and come back, readjust it. I may explore putting the extra components in for the DC offset adjustment. But what I might try is substituting this 250 ohm out for a 500 ohm and see if it still actually works. Just because I don't like the physical size of this thing. Just give me a minute. The 500 ohm trimmer is in, and I'm going to say yes. I hope I'm not boring anyone with this video, but I just like to be a little bit more complete. So if I turn the pot, as we can see, the bias is starting to go up. So the value of that trim pot is not overly critical, and I've also found out that its maximum is still 34 mA on this supply voltage. So it's obvious that this potentiometer is not overly critical, as long as it's not too high, of course. So I might stick to 500 ohm. 25 mA of quiescent current is, yeah, okay with me. Although the supplier says more like 20, but whatever. So I'm going to let that stabilise for 5 minutes, come back and check it, and readjust as necessary. So, yep. Well, it's been a fair few minutes, about 6 minutes or so I think it is, and the current's come up a little. That's only because of ambient temperature and that the transistor isn't actually in contact with any of the drivers, which it should be to correctly monitor the heat. So if I just touch the transistor body, It is slowly coming down as the heat from my finger is adjusting the junction temperature. Not by much though. If I release my finger, it starts to climb back up. So I'm going to drop that bias down a little, now that I know that it works, to about 25 mA, about there. Just touch that transistor again, it's dropping off, good. Release, sorry about the camera, coming back up. Alright, excellent. So here's the plan. I don't really have one. I'm going to do a power output test at the current supply rails. I'm going to have to change the current limiting, obviously, just to see how much power this thing can produce into 8 ohms and 4 ohms. Then I might do a quick dirty frequency response test, and then finally a sound test. But what I want to do is probably include the circuitry for the offset nulling and the VI limiter circuitry, because I don't even have the flyback diodes installed yet. I just ran out of time yesterday. I wanted to get the basics of the amplifier built and test it and sort the problems out first before worrying about all the extra circuitry. So for now I'm going to do a power output test. Dummy load is connected as 8 ohms. I've got a ×1 probe on the input just so we can see what the voltage going into the circuit is, so we know what its input sensitivity is. I'm going to change the current limit to 2 amps, should be fine for this. So with it loaded and nothing shorting as far as I can see, I'm going to apply power and see if anything goes up with a bang. I shouldn't really be leaning over it whilst doing this, but anyway. Jolly good. No bangs, no sparks, no nothing. And 19 mA of current being drawn by the main supply, and as we can see there, which is fine, I suppose. Right, so I'm going to turn the oscillator back on, but I'm going to let you watch the circuit because I want to see if these output transistors explode. Because they came off of another amplifier which I didn't trust them on, the AL200, which the BTL amplifier, which blew the TIP 35 and 36C output transistors up on. So I'm going to run. I can see we've got an output. I can hear it screaming through the load. I don't seem to see any input though. There we go, there's full clipping. I don't want to do that into the load too long because the output stage may overheat because this bracket's not substantial enough. We've got 17 volt RMS coming out. Not bad, 36 watts considering the power supply rails. It probably would fare better with a paralleled output stage, but I haven't got that far yet. So for some reason I wasn't seeing our input sensitivity. Maybe because this is ended up in ×10 or something stupid. No, it's in ×1. We are measuring the right point. Okay, maybe the voltage per division is wrong for that input. Yeah, okay. Right, so I'll crank that back up to, whoa. Huh. That's got to be a grounding issue. Alright, so I can't even measure the input sensitivity at the moment. Well, that's kind of annoying. Let's see, I'll remove the ground on that probe so that it's using the ground of the output rather than the ground where I've got it. Yeah, 412 millivolt RMS in. That may or may not be right. So what I might do is I'll disconnect my output probe. Yeah, no, it seems about right. Okay. Yeah, there was a bit of heat going to that, not much. Alright, so I might change over to 4 ohms, and I'm going to be daring. I'm going to actually do this with it powered up. The oscillator's down. The current did actually shoot up a bit. That's only because it's loaded differently. We're now at like 31 mA instead of 27, which it was on the 8. So into 4, let's ramp this up, watch for explosions. Got an output, which is good. It's more like only 10 volt RMS. Yeah, that doesn't seem right. Yeah, because we're only getting a measly 25 watts. Yeah, that just don't seem right. I would have expected more out of the supply, unless it was current limiting, of course. I'll just disconnect that input probe now, I don't need it. I will wind the wick up and see if we are going into current limiting. Apparently we are. So it's not the top supply that's going into current limiting, it's the bottom one. So I'm going to ramp that way up. Again, you can look for any sparks. Well, that's a bit better. We're not current limiting. Everything's good there. More like close to 14 volt RMS, 13.4. It's not much of an improvement. Actually, correction it is, because it's more like 44 watts now into 4 ohms versus the 36 into 8. That seems much more realistic. So, good. That is starting to get quite warm. Well, that was a pop on the circuit board. Those drivers are getting warm, so it might be in my best interest to put a small heatsink on them before continuing further testing. So I'm going to turn the supplies off, and I'm not going to do any more 4 ohm tests anyway. These transistors, they're fine, but those were becoming a concern. Okay, so let me hook on a couple of heat sinks here somehow without it shorting on shit, and what I'm going to do then is do a frequency response test. It's 20 past 8 in the morning, guys. I mean, yeah, I'm not exactly awake yet. Okay, those drivers have a couple of little thin heat sinks on it just to help keep it cool, especially during further testing. I really, when doing things like this, need to keep monitoring transistors to make sure they're not overheating. I've got that mini oscillator set to roughly a kilohertz. It's not connected to the input of the amplifier because there's no way to turn it off. So I'm going to set the camera up somewhere where it can see the oscilloscope, and you can watch that, and we'll do the frequency response test. Connect the oscillator, ignore the fact that it's triangular. So for a base reference, we've got 7.33 volt at 1 kilohertz roughly. So I'll go down. Not much is changing. Good. Down in frequency, I'll just change that. We've actually got a slight increase towards 100 Hertz, 150 in this case, from the 7.33 to 7.44. So if I go up in frequency now, it is starting to roll off a bit, but again that could be because of breadboard. So I'm going to go right down to 10 Hertz and get this to draw correctly. That looks terrible at 10 Hertz, just monitoring heatsink temperature. So I'll increase it. Well, it wasn't even 10 Hertz, it was more like 7 Hertz. Where are we? Right, we're at 10 Hertz now. got a reduction in voltage. The signal looks weird, so I'll get it up to 20 when it so wants to. There we go, there's roughly 20. Yeah, it starts to roll off under 100 Hertz, unfortunately. Again, that could be the breadboard. So I'll go up to around the 30 Hertz mark is where the voltage starts coming back up, and the signal starts to look more like it originally did at 1 kilohertz, which is triangular obviously, or sawtooth, what do you want to call it. So, okay, I'm going to put this at roughly 30 Hertz at the moment. So I'm going to go way up in frequency now to 3 kilohertz to see what our upper frequency is. As you can see, the voltage has dropped by about 300 odd millivolt the higher it goes. It is rolling off. It's not exactly flat as I would like it. They're now still considerably rolling off at 20 Hertz, 20 kilohertz rather, and it sort of like buggers off at 88 kilohertz. At least I think that's 88 kilohertz. Yeah, roughly. Yeah, it really buggers off at the 30 kilohertz mark. Okay, well, we know roughly from this breadboard experiment what our frequency response is. It's not exactly flat, it could be better. Again, it could be due to the breadboard layout as well as other factors beyond my control here. If it was on a proper PCB, it'd probably be more flatter, which excuse me, which will be the next thing for this, is to route a new PCB, because I'm not using the TO3 output devices that were originally specified, and do a proper frequency response test on it, and do a proper power test on it with parallel output stage as well as plus minus 42 volt rails. So that heatsink is getting kind of warm, so I'm going to kill that. And I'm really glad I did put 2 heatsinks on these drivers, because they are slightly warm. So, but that was getting considerably hot. But at least our quiescent current has dropped back off to 20 mA. So, well and good, I suppose. So what's next? Well, I think I might include the VI limiting components just to see if they play nice with the circuit, and we still get full output power into 8 ohms, for instance, and the flyback diodes. Plus I might also install the DC offset null components for pins 1 and 8, and yeah, just so we've got some way of controlling that. So let me get busy doing some extra wiring and messing about off camera, and we'll come back in just a moment. I thought I would start simply and just do the DC offset adjustment pot first before the VI limiter. So I've got that cobbled in there, not that it's really needed, but it does serve a purpose. So with the circuit turned on and the pot not adjusted since I put it in the breadboard from wherever it was adjusted last, I'm going to turn the pot excuse me, one way. That appears to be going up. Alright, so we've got 22 now millivolts. Go the other way and it's coming down. So that's doing what it's supposed to be doing, as far as I can tell at this stage. I'll wind it anti-clockwise in this case, further and further, down to about 7 millivolt, 6, 5. Wow, that pot was really rotated far up. Can't get in there either. Story of my life. I have reached the end of the travel of the pot and I can't go any further than 5 millivolts. So I'm wondering if it's actually worth even doing. So what happens if I disconnect it? One side's been disconnected, other side's been disconnected. Falls back to 0, or close to it. I might actually leave that component out, to be honest, because it wasn't in the original circuit and it doesn't seem to be providing me any real benefit. So yeah, I think I will just leave those components out of circuit and not worry about it too much. So I'll get on to doing the VI limiter and the flyback diodes. Test we still have an output, everything's happy, and then we'll finish up with a sound test. And that's this amplifier tested to its fullest that I can do on the current power supply. Well, a short time later, as messy as that looks, it looks kind of like a bad Frankenstein's hairdo. There's the VI limiter installed, and ignore this component off here, that's not part of anything. I haven't installed the flyback diodes because one, there's not enough points left on the output now to make it work, and second, the thickness of the lead on the 1N5408 is too thick to go into the breadboard. So for the testing purposes of making sure that the VI limiter is not causing issues with the amplifier, those flyback diodes aren't really needed. They're only needed in the event of a short circuit, which I'm not going to do on the breadboard for obvious reasons. So currently the power supplies are off, or they're not connected in, like turned on for the load. There we go, no issue so far. No weird activity on the scope. No smoke, which is always a good sign. Just checking things for heating. I can't get to those transistors really. That notification just made me jump a little bit. Always when I'm doing something a little bit intricate, like feeling around a live circuit, and my phone makes a loud noise. Okay, now I need to connect the oscillator back up to the input, and well, we don't appear to have an output for some reason. We should do. I haven't done anything. It might actually help if I connected the bloody load to the circuit. So for now I'll turn this off whilst doing it. Sometimes I just feel like an idiot. So output and ground, we're at 8 ohms. Turn it back on. No unusual loading. Again, nothing unusual on the scope, even though that's invalid because it wasn't even connected the last time. Again, checking things for heating now that the load's connected. Nothing appears to be getting hot. Right, now I'll reconnect the oscillator. If I can get in there now. Nice, we've got signal. I'm going to change back to 1 kilohertz because that's just way too high of a frequency. Close enough. Get some amplitude. Yeah, it's working and clipping, and the VI limiter is not really doing anything to the circuit. Right, excellent. Disconnect that now. Next thing I want to do, the final thing I want to do, is that for a start, and secondly connect a speaker up to it, but I won't power the unit up with the speaker connected. I'll connect the speaker after it's been powered, just, you know, to imitate a muting relay, because I don't really want any turn on transients, pops and noises and shit coming from the power supplies turning on, damaging my speaker. We'll just, with the input disconnected, listen for any unusual noise. So let me clean up a bit, put the load away, disconnect the scope, turn some stuff off, and hook up a speaker, or we'll get one ready to hook up, and we'll see what happens. Alright, the speaker is ready to go, so I'll turn my supplies back on. I'll just touch this lead to the positive. Don't hear anything unusual, that's good. Let's see it. Oh, there's a bit of a hiss coming out of it. It's not exactly quiet amplifier, but there's no circuit noise. Bonza. Yep. Excellent. Alright, I need to cook up a music source, etc. Actually, let's just see something. Yeah, so I'm not going to do that too much to the speaker, so I will have my lead disconnected before I'm turning on or off the amplifier. Okay, so let me cook up some music to it and we'll see how it sounds, and then we can end this video. Okay, let's play a bit of audio.
My fellow Americans, I, Donald J. Trump, President of the United States of Trump, am here today to announce that I am waging war on my underwear. I just farted, and it smelled bad, real bad, so bad, that even skunks are afraid of me.
Just used a Trump AI voice generator for that. I'm just being silly. So I'll actually go into some actual music and we'll have a listen to how this actually sounds. It sounds alright from what I can hear, so that's fine, but here we go. Okay, that should do for that. I'll just try another track whilst I'm at it. Okay. Okay, I'm happy with that. It is sounding a little bit crisp on the highs. That could be because of the 100 nanofarad capacitor across the 47 microfarad capacitor in the negative feedback path of the op amp there. But a circuit that was published like 30 years ago, 1995 now, in Electronics magazine, where I only had to modify the protection circuit a little bit to make it work at a different voltage, but didn't really have to do much modification to the amplifier to get it to work, apart from, well, two capacitors. The 33 picofarad that went across pins 1 and 5 there is now a 10 nanofarad to stop it from oscillating, and the 33 nanofarad in the Zobel network there has been changed to a 100 nanofarad. Two changes, two capacitors, but the rest of it works. I call that a win. So I'm going to end this video here. They are getting considerably warm. I'm glad I put heat sinks on them there. These drivers are supposed to be mounted to the same heatsink as the main drivers, output transistors, which aren't even getting warm, but the drivers are. So if you were to build this circuit up yourself at home on, say, breadboard, or well, not breadboard, but on Veriboard or something like that, be considerate of the fact that these two driver transistors do need to be heat sinked, or you can be in a bit of trouble. And the VBE multiplier must be in contact with the drivers at least for this VBE multiplier or bias spreader to actually track the drivers, so it can lower the quiescent current accordingly. I wouldn't run the 100 mA that he specified. That's just way too high, and all that's going to do is dump a shitload of heat into the heatsink unnecessarily when it's idle. Why do that? It seems to operate fine at 25 mA, 35 mA would be good as well, even 40 mA. It depends on the supply voltage and how far the VBE multiplier will adjust down to in current for you to choose what current to operate it at. But looking at it on the scope, even down as low as 20 mA, it was not suffering crossover distortion, so I call that a win also. Anyway, hope you enjoyed this video. Yes, I know it was kind of a long one, but I wanted to be really thorough with it and bring you along for the journey. I hope you enjoyed it. So I'm going to end this video right now. I'm the Astro 30, and if you enjoyed this video, please remember to go down below, like, comment and subscribe if you haven't done so already. And as always, this is the Astro 30 saying see ya, thanks for watching, have a great day.